Okay, let's talk about these now. As I was saying, thermochemical equations talk about enthalpy, and let's talk about what enthalpy is. Remember, enthalpy just means changes in heat. Now, we can't measure heat directly. You think we can? Oh, we can just measure the temperature. No. Remember what temperature measures. Temperature measures how fast the particles are moving. We can't measure directly how much heat something has. What we can measure, though, is how much energy changes there are. We can measure changes in enthalpy. So that's what the delta stands for, the change in heat. And it's measured, notice here, oops, what did I do? I turned it off instead of on. Let me turn it back on. This notation right here, this means the change in enthalpy, change in heat, is measured in kilojoules per mole. Kilojoules per mole. And this negative in front means that heat is released. So this is exothermic. It's given off to the surroundings. So this is a combustion reaction. You should know that. We have a hydrocarbon plus oxygen. It gives off carbon dioxide, water, and then it releases to the surroundings heat. So it's exothermic. Okay, and then because this, we can say that for each mole of methane, or for each 2 moles of oxygen, now this isn't as important, and it releases per mole of carbon dioxide produced and per 2 moles of water produced. That's not as important as some of the other that we're going to be doing, but I would want you to see that it can be used as conversion factors. That's showing you conversion factors. So I hope that's going to give you a glimpse of what you're going to be doing. And you're going to be doing conversion factors. You're going to be using a dimensional analysis. Okay. Now, you will be needing whether it's solid, liquid, or gas for these, and you will need to know how many moles, because in order to do dimensional analysis, you'll have to use that for the conversion factor. Now, you're not going to have to worry about knowing these delta H's. There's a table in the back of your book, at Appendix 2, I believe it is, in the back of your textbook, that has these delta H values for you. Just make very, very sure that you use the delta H. There's a delta H value, which is enthalpy, and then there is a delta G value, which stands for Gibbs free energy, which is a Chem 2 topic. Okay? We're good there? Please notice this one. Water from a solid to water to a liquid. This, you know, is going to be endothermic. I hope you know that in order to go from a solid to a liquid, you have to heat it up. So this requires some energy. You have to add energy to this to make it happen. So this is endothermic, and you can see how much energy that you have to add here. You have to add 6.01 kilojoules per mole. Notice that this is a solid and this is a liquid. Now we're still talking about water here, but just to make something go from a solid to a liquid, water in this case. All right. This is what's required. Yeah? And so you can see here the calculation. And then it's showing you in this next bracket here, but what if we had 2 waters that we wanted to convert? Well, then we'd also have to multiply our delta H value by 2. All right. We're good there? That's, I think, pretty straightforward, I hope, for you. And what if you reverse it? What if instead of a combustion reaction, what if we wanted to try to make some methane gas from carbon dioxide and water, and now we want to try to make some methane? Can you see that where the combustion reaction to produce carbon dioxide and water was exothermic? It gave off heat. Now, if we reverse the reaction, it becomes endothermic. You have to add energy to make that happen. Okay? All right. Here's a sample problem. Here's photosynthesis. You have water and carbon dioxide, and it produces sugar, glucose, plus oxygen. Notice, please, this is extremely endothermic. Look how much energy that the sun has to give to make this reaction happen. This reaction requires 2,803 kilojoules for every mole. It asks you to calculate the amount of energy required to make 75 grams of glucose, of sugar. So, first step that she did, this would have personally been my last step, but the first step that she did was find out how many moles of sugar this is. So let's do that. That's how much sugar, how many moles of sugar that there are, and then that's supposed to be an A right there. Then we're going to save this for later. Okay, so that's how many moles of sugar there are. All right, and let's go to this next slide then. Okay, and then for every, here's our balanced equation here, and here's the balanced equation for the reaction occurring, and we know that here's the delta H value. So your conversion factor for this would have been, is since we are talking about glucose in this case, yeah, for every 1 mole of this, it requires 2,803 kilojoules for every 1 mole of sugar that is produced. Which means that if you were to multiply that 0.416 through there to get this 0.416 mole of glucose, that you get 1.17 times 10 to the third kilojoules. Now that's certainly one way to go about it. I personally would have said, I believe I would have just said 2,803 kilojoules and then used that conversion factor. But I think you're going to get the same answer regardless of which way that you do it. But that's okay. You're still just using dimensional analysis. All right. Now, the last topic that we're going to talk about in this chapter is calorimetry. And this is literally how our food calories are determined in laboratories. How I was using a Snicker bar in the last video. So let's continue that with this video as well. How do they determine how many calories there are in our food, like a Snicker or whatever kind of food it is? We need to know the definition of specific heat. That's an important term right there. I want you to think with me for a minute. If you were to take a piece of aluminum foil and you wanted to heat a piece of pizza in the oven, you didn't have a microwave or whatever, and you put a piece of pizza on top of that piece of aluminum foil and stuck it in the oven, almost the second that you got it out of the oven, you could touch that piece of aluminum foil. Now, you could not touch the pizza, but almost the second that you took it out of the oven, you could touch the sides of the piece of aluminum foil. You would never, ever do that if it was an iron skillet. And you would never put a pan of boiling water, or put a pan of water in the oven for 10 minutes and pull it out and touch it. Never. But aluminum foil, stick it in the oven for 10 minutes, and you could pull it out almost with your hands, and that would be fine. That has everything to do with the specific heat. Specific heat is the amount of heat energy that's needed to raise the temperature of 1 gram of that substance by 1 degree Celsius. It just so happens that the specific heat for things like aluminum foil and a lot of other things, mud, sand, sand is very high, but not mud, not soil is not very high. There's things that have a very low specific heat, and then there are things like water that have an extremely high specific heat. And then there is heat capacity. Now, think of heat capacity as thermal energy. Heat capacity is, okay, I don't just have 1 gram of that thing, I have a bunch. I'm going to draw my little cup again. I got a little cup of that object, and I got a whole big bowl. How long is it, or how much energy is it going to take me to heat up that little cup versus the whole bowl? How much energy is it going to require to raise the temperature of just a little cup versus the whole bowl? That's the difference between heat, specific heat, and heat capacity. Specific heat is narrowing it down and dividing it by how much do I have. So it's per gram. It's per gram for specific heat. Heat capacity is saying, well, let me multiply that by how many grams do I have. So if I want to heat up the whole thing, then it's going to cost me more energy. So that's the difference between the two. Specific heat is per gram, and heat capacity is how much energy is it going to cost me for everybody to go to the park. You know, think of specific heat is how much is the cost per ticket, and heat capacity is how much will it cost me for everybody to go. Here's an example. Specific heat of water, which this is just one more piece of evidence for me that there was a grand design in the design of our earth, because water has one of the largest specific heats of any substance known, absolutely, hands down. And our earth is almost 80% water. And if that were not so, that it had such a huge specific heat, that on days like today, when it is beautiful outside, and yet yesterday, it was fairly chilly, or was it Saturday that was fairly chilly all day, our temperature on the earth would swing so wildly that nothing could stay constant. And yet, specific heat of water is so high that the temperature of our ocean stays at a fairly constant rate. And so that's all due to the specific heat of water. So the specific heat of water is 4.184. The specific heat of aluminum is about 0.15. So it's a huge, huge difference. Water takes an enormous amount of energy to change and to boil. So it's a very unique substance in a lot of ways. Okay? I will expect you to know the specific heat of water. It is not an accident that the specific heat of water is 4.184 joules, and it takes 4.184 joules to equal 1 calorie. Mr. James Prescott Joule was a very smart man, and that was done on purpose. So they set that to be equivalent on purpose. So we can find the specific heat in a substance. The specific heat is given with the letter Q. So the specific heat of a substance is equal to, and you need to know this right here, the specific heat in a substance, the specific heat is denoted with an S. M is for the mass of the object, and T, delta T right here, is the change in temperature, Celsius degrees. Okay? We're good there? And then the other one that you need to know is simply C, and then this is delta T. Okay? And this is a big C for heat capacity. We're going to work just a couple of problems on this, and that's the last thing that we're going to cover in this semester. Look at their aluminum. Oh, I had aluminum and gold mixed up, their heat capacities. Aluminum is 0.9. It's gold, that's about 0.15, and it's 0.13. So there you go. Aluminum has a very, very low specific heat. One of the lowest, and then water is one of the highest heat capacity, specific heats. Okay? You have this table also in your textbook. You will not be asked to memorize any of these except for water, and water is an important one to know. It asks us in sample problem 5.4 to calculate the amount of heat that's needed to raise the temperature of 255 grams of water from 25.2 degrees Celsius to 90.5 degrees Celsius. So let's work this one very quickly. So we're going to use this formula, the Q one. Q is equal to the mass of our water times the specific heat of water times the change in temperature of our water. So our mass of water was 255 grams. The specific heat of our water is 4.184 joules for every gram and every degree Celsius. And then our temperature change, we're going to subtract, I'm up here on my scratch paper, 90.5 degrees Celsius minus 25.2 degrees Celsius. And that's 3 right there, and borrow that, make that an 8, that's a 5, and that's a 6, 65.3. Notice this degree Celsius takes out that degree Celsius, and this gram right here takes out that gram right there. And so then we're simply going to multiply to get our answer. We're going to take 255 times 4.184 times 65.3, and I got 69,669.9 joules. And it asks for it in kilojoules, so we're simply going to divide that by 1,000 to take it into kilojoules, which means 69.7 kilojoules. So that would be our answer. Okay, our answer would be 69.7 kilojoules. We have 3 sig figs in our given there, so that's how many sig figs we need in our answer. 69.7 would be our answer there. So that's not too bad. I think these are kind of fun. I like them, and that's exactly what Dr. Burdg there got. And so you can see those are kind of fun. Okay? And then here is how exactly our our food calories are determined. They take a much fancier bomb calorimeter than this. They use a bomb calorimeter, and literally they would blow up a very small sample of your food, and they would do it inside of a water bath so that it's surrounded in a water bath, and they would measure the temperature of the water before and see how much does the water temperature raise, and they would do exactly what we just did. How much was the temperature before? How much was the temperature after? How many grams of water were there inside this calorimeter, this chamber? And so what caused the temperature of the water to raise? The food literally burning. And so however much water there was, now they know how many calories, the temperature increase there was. Now they know how much energy it required to do that, and they can calculate then how many calories that was, because they changed from joules into calories, and that's how they determine the calories that are in our food, and they do it in nutritional or kilocalories so that it looks a little nicer on the back of a package. Yeah? That's exactly what they do. Okay? And this is exactly what they would do. Okay? And here we're using the law of conservation of energy, or the first law of thermodynamics, and you would set that equal, these two equal to each other, because you know whatever heat is lost is going to be gained by the other. So I can go back to this to show you that says that whatever heat is lost from our calorimeter is going to be gained from, whatever heat is lost from the burning or the heating up of the pellet is going to be gained from the water. Just like with our food, whatever's lost from burning our food is going to be gained from that water. That's exactly what this is saying. And so you have this metal pellet, and it was originally at that temperature, and it's dropped into 125 grams of water. That's originally at that temperature. The final temperature of both is 33.1. So we're going to set this up, and I'm going to show you. This is the last problem that we're going to work on. The last thing that we'll do right here, and we'll be done. Okay? It says, so we have both. If we took, we know that we have the specific heat of the metal. So we know that, let's just work with the metal pellet right now. We know that you have 100 grams of it times its specific heat of the copper, whatever metal pellet it is. Does it say what its specific heat is? No. Oh, we're looking for the heat capacity. Okay. And then its change in temperature, it started out at 88.4 and it ended up at 31.3. If we subtract those two, 88.4 minus 31.3, that's a 1 and that's a 7 and that's a 5, 57.1. So the change in temperature for it was 57.1 degrees Celsius. Yep. And what about our water? Our water on this other side, we know its specific heat capacity is 4.184 joules, and we know it started out at 25 degrees and it ended up at 31.3. So let's go 31.3 minus 25.1. That's a 2. That's a 2. Carry the 1. 11 minus 5 is 6. So it only raised its temperature 6.2 degrees. So its delta T is 6.2 degrees Celsius. And this is per gram per degree Celsius. And then it had 125 grams. So this was times 125 grams. I'm running out of space here. Times 125 grams, yes? So we're going to multiply that gram, took out that gram, that Celsius. Oh goodness, what did I do now? That Celsius took out that Celsius, and so you can see when we set them up on each side, we can find, you see what I did on each side? We could find the heat absorbed, and we could then find, okay, we could find the heat capacity of the pellet. Okay, we're looking for the joules per Celsius of the pellet. Okay, by setting that up. Okay, and this is exactly how a bomb calorimeter. You put your little piece of food down in here where the little yellow piece is. Well, that's your sample cup. This is how an actual bomb calorimeter that you would burn food or something of the sort in would look. All right. And this is exactly, here's a sample problem for a bomb calorimeter. Okay, and here's a little cookie that they put in a bomb calorimeter. I'm not going to ask you to work this one unless you just choose to. It is in your textbook, and you can see exactly how it's done. But I believe that we have fulfilled the requirements. That, by the way, that RXN simply is the chemistry way to say reaction. Okay? Because I believe we have fulfilled the requirements for the course. And so we have talked about calorimetry. It's worked exactly the same as the last problem that we did. So you all have a great time doing your problems. I'll put some up for you.